Hello and welcome to your naive Bayes and Python lecture. So first I'm going to start off with what we should always start off with when opening a new notebook, and that is running all of my import statements. So I'm going to go ahead and run that. Don't worry about this line. This is just to make sure that my numbers print out instead of using scientific notation. So we are going to be talking about how to implement the naive Bayes algorithm. And so to do that, I'm going to go ahead and load in this spam data set, which, like we talked about in the theoretical lecture, is looking at whether or not an email is spam based on whether certain words are present. Cool. So you can see that our data set consists entirely of binary variables. We have whether or not an email is spam, 0 or 1. We have whether or not the word Viagra appears, the word love appears, the word dollar appears, or the word buy appears. And we're going to use those predictors to predict whether or not an email is spam. Okay, so normally you would do this with all of your data, but obviously for the sake of time, I'm just going to do it with one. And I'm going to make a graph to explore our data a little bit. So I'm going to give it that spam data frame. And I'm going to say AES X equals factor is spam. And remember, factor just tells ggplot that the zeros and ones in this column actually represent categories, not numeric values. And then I'm just, for the sake of it, going to say fill equals factor Viagra. So this is going to show us for both the spam and the non-spam emails what proportion of them have the word Viagra in it. So I'm going to add a geom bar. And then, of course, for aesthetic purposes, a theme BW. Cool. So when we run this, you can see that we actually have the same number of spam and non-spam emails. There's 100 of each in our data set. And you can see that when an email is spam, it is much more likely to have the word Viagra in it, which makes sense because you would think that people sending you spam emails use that word more than, your personal correspondence. So now that we've explored our data, let's go ahead and build a model. So now that we've explored our data, we're going to go ahead and build a model. And the first thing that we have to do is specify what our predictors and our outcome are. So first we'll do X, and X is going to be all of the features in our model. So Viagra, love, dollar, buy. So let's select those columns. Viagra, love, dollar, buy. And then of course we have to specify our outcome, the thing that we're predicting. So we'll say spam is spam. Cool. So now that we have our X and Y variables, let's choose our method of model validation. In this case, I think I'm going to use 5-fold cross-validation. So let's make our k-fold, and splits equals 5. And then we have to set everything up for that for loop to do our k-fold cross-validation. So I'm going to say ACK because we're going to store the accuracy. Remember, naive Bayes is a classification algorithm, which means it's predicting a category. So we usually use something like accuracy to see how well it did. So I'm going to create an empty list for that. And then I am going to create our model. So I'm going to say NB for naive Bayes is a Bernoulli NB. So that is the naive Bayes algorithm that we're going to use because all of our predictors are binary variables. I'll talk a little bit more about this at the end. For now, you can just trust me. So we're going to create our model, and then we can say for train test in kf.split x. And then as typical, we are going to go ahead and set up our X train and Y train. I'll be back when I've done that. Okay, so now that we've set up our X train and our X test, I actually realized we're going to want to store both our train accuracy and our test accuracy. So that ACT list that we did, I'm going to say ACT train. So that's going to be where we store our training accuracy, and ACT test, that's going to be where we store our test accuracy. Okay, so now that we have our train and test inside of our k-fold method, we would normally at this point think about z-scoring. but we only have binary variables, so we're going to skip that step because we don't z-score binary variables. So then the next step is to take our model and say model.fit and fit on our training data. So now that we have a beautifully fit model, we can go ahead and look at the model performance. So we're going to do that really in 3 ways. First, we are going to append to our accuracy training data. So we're going to say acctrain.append. And then remember, we are going to calculate an accuracy score. So we're going to say accuracy score, and we give it the real data. So that would be ytrain in this case. And then the predicted data, which we're going to grab from our model, nb.predict xtrain. So this is going to compare the predictions from our model versus the actual values for the training set. And then we can go ahead and copy and paste this and just change it to be for our test set. So we're going to say actest, and then we're going to say ytest and xtest. And then the last way that we sometimes look at our performance of our model is with a confusion matrix. So I'm going to plot the confusion matrix for our test set. And so remember that plot confusion matrix takes the fitted model, the x test, and the y test, and it'll create that beautiful confusion matrix for you. Awesome. So our for loop is done, and once this for loop has done all of its rounds, so it's going to do 5 models because it's 5-fold cross-validation, we can go ahead and print out the average accuracy for our train and our test set. The confusion matrix will actually output every time we run it, so it should already be there. So to do that, I'm going to use this fancy formatting. I'm just going to print out test acc and then turn the mean accuracy into a string. Cool, so we have everything set up for our model. All we need to do is run it. So once we get our model accuracy and all of the confusion matrices, we can now examine how well our model did and check for overfitting. So you can see that the average test accuracy was 90.5%, and the average train accuracy was also 90.5%. And that's good news for us because when we're looking for overfitting, we're basically looking for a case where the train accuracy is a lot higher than the test set accuracy, which would indicate overfitting, but we don't see that here. In fact, the estimates are exactly the same. So it looks like we're on a good path here. The next thing we can look through is the confusion matrices. And I'm just going to focus on this last one, but we are just trying to make sure that there are no patterns that are concerning to us. So this looks pretty good. We can see, as our accuracy scores said, that our model is doing pretty well, and it's not the case that our model is for some reason predicting only 1s or only 0s or anything like that. So we don't see anything weird in this confusion matrix, so I'm going to give it the A-OK and move on. So the next thing that I want to do is check a single email by hand using our model. So let's pretend we got this email. Hello, I hope you are well. Honestly, I am doing super well. I have the urge to buy something crazy. Maybe one of those giant bean bags from the mall, a love sack. Well, another day, another dollar. Sincerely, Dad. So we can imagine that we received this email and we are going to try and classify it as spam, being a spam email, or ham, being a true email from your dad. And we can use the fitted model that we got from the previous part to do that. And so we can do this by saying, okay, let's convert this actual email into data. So remember, we're looking for the words Viagra, love, dollar, and buy. And so Viagra does not, fortunately, appear in this email. The word love does, the word dollar does, and the word buy does. So this is essentially what this row of data would look like if this email were in our data set. And so we can take that, and don't worry too much about this. This is just making sure that we have an array of our data so that we can predict from it. So we're using our old model. We're putting in the new data that we just by hand calculated from this email. And we're going to see what the model thinks the prediction is. Is it spam or is it ham? So when we run this, you can see that this algorithm thinks, perhaps rightfully so, that this email is spam. Now let's actually do some of the math by hand. So we're going to use spam, our data frame, and this function group by, and we're going to say group by is spam, and then use the .mean function to pull the proportion of emails that have love, Viagra, etc. for our spam and our non-spam emails. And when we run this, hopefully this looks pretty familiar because this should be similar to what you saw in your theoretical lecture. Okay, so now that we have this table, let's go ahead and use these probabilities to predict whether this email is spam or ham. So first I'm going to go with spam, and I'm going to call this spam score. Yep, score, there we go. And so remember, the naive Bayes algorithm says that the first thing that we have to do is multiply all of our probabilities together. So for something that is spam, we're going to be looking at this bottom row because 1 is spam. So remember, our email did not have the word Viagra in it. So this is the probability that a spam email has the word Viagra. So we need to say 1 minus 0.32 to get the probability of a spam email not having the word Viagra. Then we're going to multiply that by the probability of having the word love, and we're going to say 0.05 times the probability of having the word dollar, which we did. So we're going to say 0.83 times the probability of having a spam email have the word buy, which ours does. So we're going to say times 0.74. And the last step of the naive Bayes algorithm is to multiply by the probability of an email being spam just in general. And we saw when we explored our data that we have equal numbers of emails that are spam and ham. So we are going to go ahead and multiply by 0.5 because exactly half of our emails are spam and half are ham. So multiply by 0.5. Then the next thing we have to do is calculate our ham score. So we're going to do the same process, but we're looking now at the probabilities that we got from the ham or real emails. So again, we do not thankfully have the word Viagra, so we're going to say 1 minus 0.03 times 0.36 times 0.02 times 0.02, and then again, the final step, multiply by the probability of an email being ham, which again is 0.5 because they're equal. So now that we have these scores calculated, I'm going to go ahead and print them out so that we can see and compare them ourselves. And remember, this is exactly what the naive Bayes algorithm is doing for us. We're just now doing all of the math by hand. So I'm going to go ahead and print it. And again, don't worry about my fancy formatting. This is just because these are very small numbers and I need to make sure that Python actually prints all of them out. So you can see here that the score for spam is much like magnitudes higher than the score for ham. So hopefully that makes a little more sense intuitively now that we've done the math by hand, why our naive Bayes algorithm put this email into the spam category, because the score that we calculated is higher for spam than it is for ham. Okay, so the last thing that I want to talk to you about is this fact that there are actually multiple algorithms, multiple functions to use naive Bayes in sklearn. So the one that we previously used is the Bernoulli naive Bayes function, but there are actually two others that are commonly used for naive Bayes. And I'll go over this in a second, but the differences between these basically have to do with what kind of data that our predictors are. So one type of function that you can use for naive Bayes is the Gaussian naive Bayes function. And that function assumes that your variables are continuous and have a normal distribution. The reason we have different functions for this is because the way we calculate those probabilities that we use for the naive Bayes calculation depends on whether your variable is continuous or categorical. The way those probabilities are calculated are different, and that's what these different functions do. So again, Gaussian naive Bayes assumes that your predictors are all continuous and have a normal distribution. The Bernoulli naive Bayes, which is what we just used, assumes that your data are binary. So that means that all of your predictors are zeros and ones. The third type of naive Bayes that you can do in sklearn is categorical naive Bayes, which is actually very similar to the Bernoulli naive Bayes that we just used, but instead of forcing you to have only 2 categories, 0 and 1, you can actually have multiple categories. So you might be asking me, okay, well, if Gaussian assumes continuous, Bernoulli assumes binary, and categorical just generally assumes that you have categorical variables, what if my data is mixed? Well, the problem with that is that you actually can't do that with a single function in sklearn. There are workarounds if you do have a mix of predictors that are continuous and categorical, and I've linked a little bit of a tutorial or like answer here. So you can go ahead and check that out if you need to use naive Bayes on a mixed predictors data set in the future. But for the purposes of our class, we're going to stick to cases where we either have all continuous or all categorical predictors, like we did in the previous example. But I'd love to show you an example with the Gaussian naive Bayes of how you can use that function when you have continuous predictors predicting a binary outcome. Okay, so the first thing that I'm going to do is I'm going to generate some fake data for us to use in our naive Bayes model. So you can see here that I'm generating our outcome. This is the binary thing that we're predicting. And then I'm generating 3 continuous predictors. Then I'm going to go ahead and put them in a data frame for us to look at. So you can see that our outcome y is a binary 0, 1 variable, and then our 3 predictors are continuous. So I'm going to set things up similar to before. First, we're going to set our x, which is going to be df bracket x1, x2, and x3. And then our y, our outcome, is just going to be the column y. So now we're going to set things up like before. We're going to do our k-fold, and splits equals 5. And then when I build my model, I'm going to call this NB2, I'm actually going to use a Gaussian naive Bayes. So we're going to say Gaussian NB, and this is instead of the Bernoulli naive Bayes function that we used previously. So like before, I'm going to store our accuracy for the train set and the accuracy for the test set. And then I'm going to do our for train comma test in kf.split x. And then as usual, I am going to go ahead and calculate my x train, x test, y train, y test. I'll be back when I do that. Okay, now that I have calculated our x train, y train, etc., now I'm going to actually go ahead and z-score my variables. Since our continuous variables actually can be z-scored, unlike our binary predictors, it is totally valid to z-score, and we want to do so in a way that doesn't cause data leakage. So I'm going to say z equals standard scalar. And then I'm going to say x train equals z dot fit transform x train. And the reason I'm doing it this way is because all of our variables are continuous and all of them are being z-scored. And then x test equals z dot transform x test. So now that we've z-scored, we can fit our model. So we'll say nb2 dot fit x train, which now has our z-scored continuous variables, y train. And then similar to before, we are going to generate all of the accuracy scores and confusion matrices that we need to evaluate our model. Cool. So you can see, just like before, we appended our test accuracy to our test accuracy list. We appended our train accuracy to our train accuracy list. And then we went ahead and we plotted the confusion matrix for each of the models that we're going to create. So now that we've set this up, it actually looks super similar to what we did before. The only difference, now we're using continuous variables, so we're using the Gaussian naive Bayes function. And because they're continuous, we are now allowed to and will z-score. So let's go ahead and run this code. So you can see we have our test accuracy on average and our train accuracy on average. We're looking at this and we're saying, is there a huge difference between training and test accuracy? And in this case, I would say there's not a huge difference. There's a slight difference. The train accuracy is a little bit higher, but it's not a huge difference that makes me go, uh-oh, I think our model is overfitting. So I'm going to give this an A-OK. We can also, again, look at our confusion matrices to make sure that there's nothing wonky going on. And at least in these, it looks like everything's okay. We do have a little bit of more errors compared to the other model that we did with the Bernoulli naive Bayes, but it's not like there's any systematic problems, and we're actually getting things right a lot of the time. Okay, so hopefully that helped you understand how we could use naive Bayes with continuous predictors. And just to review, there are those three functions we talked about: Gaussian naive Bayes, which is for continuous predictors; Bernoulli naive Bayes, which is for binary predictors; and categorical naive Bayes, which is for categorical predictors. And again, for our purposes, we're going to stick to cases where we have all of one data type, but if you're interested in seeing how you can mess around with the code to actually include a mix of predictors, you can check out that link that I posted here. Cool. Well, hope that was helpful, and I will see you in class. Bye, guys.